In many of the recent videos, we've been taking a specific look at limits. We've been sort of focusing on limits and defining them and showing examples and even creating what we've called categorical constructions. So that is limits over particular types of diagrams in different types of categories. And so we're going to kind of conclude our discussion about limits. Obviously, limits are very important, so they'll come up a lot in the future still, but we're going to sort of finish our specific focus on limits by proving a theorem about the existence of limits. So obviously, we can't guarantee that any diagram in any category is going to have a limit, right? A limit has quite a few conditions in order to define it. So it's not always the easiest thing to find a limit for any particular diagram. But we're going to look at a situation where we can guarantee the existence of a limit, and that's captured in the following theorem. So the theorem says that if C is a category with equalizers, and D is any diagram in C, so that is a functor going from some index category J into our category C, if the product over the diagram of nodes of D and the product over the diagram of arrows of D both exist in C, then the limit of D exists in C. So obviously we'll need to define the diagram of nodes and the diagram of arrows, and we'll do that in a second. But we should just note that this will probably be one of the longest proofs that we've done so far in any of the videos. So I'm going to try splitting up the sort of mathematical algebraic part of things and the diagram part of things. I'll try to sort of flip back and forth in between. So hopefully that works okay. So let's define these two diagrams here. The diagram of nodes of D is going to be pretty straightforward. So we're going to call it maybe curly n of D. So this is a diagram of nodes of D. So what are the nodes of D? Well, the nodes of D are all of the images of all of the objects in our index category, right? So our index category is J, and if we take the collection of objects that we get from just applying D to every object in our index category, then we get our node diagram. So it's just going to be a collection of objects, and obviously their associated identities as always. Now, to define the diagram of arrows, you would think that would be maybe a bunch of morphisms or something, but that is actually also going to be a collection of objects. So the arrow diagram, or the diagram of arrows of D, which we might call curly A of D, is the same. It's going to be D applied to a bunch of objects J. But what are the objects J this time? It's all of the codomains for any of the morphisms in J. So basically, if we have three morphisms coming into J in our index category, and we'll see an example in a second, if we have three morphisms coming into J, that is three morphisms where the codomain of the morphism is J, then we'll have three copies of the image of J in this arrow diagram or diagram of arrows. So it's a little bit of a funny construction, but basically it's just one copy of the image of J anytime J is the codomain of a morphism. And if there's more than one morphism, then we do more than one copy of DJ. And remember, that's okay because we're in a diagram. So the morphism doesn't have to be injective. We can have multiple copies of the same label on the node. So if we draw the situation out, obviously we can't draw every possible case of every possible diagram, right? So the theorem is applicable to any possible diagram, but we're just going to look at one particular case when we draw it out, and then we'll use sort of the intuition from this one case to prove the general case. So here we have our diagram D, right? So this is going from our index category J here into our category C over here. And so that's this here, C is here, and these, as we're going to see, are also part of C. And so remember that D does not have to be injective. That's what we just said, right? A functor for a diagram can be anything, so it doesn't have to be injective. So let's look at a situation where we don't have an injective functor for the objects in the category, right? So here, D is mapping both A and C into the same object over here, dA equals dC, right? This is the same object, which is the image under D of both A and C. And then we have our other object B over here, which gets mapped to dB. And the two morphisms that are coming in, alpha 1 and alpha 2, that are coming into B here are d alpha 1 and d alpha 2 over here. And since now these are the same object, they're both parallel morphisms in this case. So hopefully that all makes sense. We're just showing an example of a non-injective diagram functor. So we'll follow this example for D throughout the proof. So now the question becomes, we need to know what the node diagram, or the diagram of nodes, and the diagram of arrows are going to look like for D. And we have them drawn up here. So if you want, maybe pause the video and confirm why this is what the diagram of nodes looks like, and this is what the diagram of arrow looks like for D. Well, the reason is because we have two nodes in our diagram D, right? We have dA equals dC, which is this node here, and we have dB, which is this node here. So pretty straightforward. We just take the two nodes and make it into a collection of objects. And remember that even though we've drawn them separately, they're still the same as they are here, right? They're just thought of as a separate diagram, right? And the same for the diagram of arrows. So we have one object for every morphism in J. So here we have alpha 1 going from A into B. So we need to have a copy of dB for that morphism, right? That's how we defined the diagram of arrows here. We need to have one copy of the object for every morphism where that object is the codomain for the morphism. And so that's what we have here. We have two arrows coming into B, but then also every object has its own identity morphism, right? Which is going to get mapped onto the identity morphisms here. So we have this node here coming from the fact that dA equals dC has an identity morphism. We have two copies of dB for the two arrows that come into B. And then we have another copy of B, obviously, for the identity on B. So hopefully that makes sense based on the definition we just found for the node diagram, or the diagram of nodes, and the diagram of arrows. And so what does our theorem say? Well, it says that if the product over the diagram of nodes and the product over the diagram of arrows both exist, then the limit of D exists. So to prove this, we would have to assume that there's a product over the diagram of nodes, a product over the diagram of arrows, and then we would have to prove that there was a limit over D here. So we've drawn the products here, and it makes sense to call them products, as we know, because products are limits over diagrams which just contain discrete objects, and implicitly their identity morphisms, but we don't really need to think about that. And the same here, right? This is just a collection of objects, so it makes sense to say that the limit over this diagram is a product. So we've drawn the product P rho dA rho dB here, and obviously rho dC is just going to be equal to rho dA. The component for dA is going to be the same as the component for dC. And then the same on this side, but the only thing to notice is that here it's doubly indexed because we're going to have multiple copies of some of these objects, right? So for this example, we need to have pi dB1 maybe for the identity, pi dB2 maybe for alpha 2 and pi db3 maybe for alpha 1, or maybe make the indexes line up to make more sense. But that's basically the idea, right? We have one projection for every copy, not just for every object like we do here. So let's start the proof by first capturing those assumptions that we just saw. So suppose C is a category with equalizers, and suppose that D is a diagram in C, where the product over the diagram of nodes of D and the product over the diagram of arrows of D both exist. Where the first one is P, which consists of a vertex P, and the projections rho j for each dj in the diagram, and Q, which consists of the vertex Q and the projections pi jn for each dj, and where the n designates which copy of dj we're referring to in the diagram. So if we go back to our drawing of the situation, we have our two products here. And one thing that's nice about these diagrams that we have, ND and AD, is that they're both just collections of objects. And since they're just collections of objects, if we want to find another cone over one of these, we don't really have to worry about any commutativity properties, right? Because a cone over a diagram has to commute with all of the morphisms in the diagram. But there's no morphisms other than identities in these diagrams, so there's no commutativity property that we need to worry about to find another cone. So all we need to do to find a cone over these is to just find one morphism going into each object, right? So given that it's fairly easy to find a cone over these diagrams, is there a cone that we could find already given this situation, other than the products themselves, right? Because obviously the products are cones, but is there another cone we could construct? Well, one thing to notice is that the codomains of all of these projections in both cases are the same, right? Like dA equals dC or dB. The only difference is that on this side we may have multiple copies of some of these objects, right? But that means that we could define a cone going from P into this diagram, the diagram of arrows, right? Because we can just reuse the components from over here, or the projections from over here, and if we have a repeating one, then we'll just use the same component multiple times, right? So all of pi db1, pi db2, pi db3, those would all be, in this case, just rho db, right? When we're going from P into this diagram. So what we can say is that we can have a cone P and then maybe call it rho j and then index it with n as well this time, but where each rho jn is just equal to rho j for all of the n's. And what are the n's? Well, the n's is less than the in-degree of dj, right? The number of morphisms that have a codomain dj, that come into dj. So let's add that here. We can say that P and rho jn is a cone over A of D, and where rho jn is just equal to rho j for all of the n less than the in-degree of dj. So I'm not going to draw it here, but you'd basically have a rho dA going here, you'd have a rho dB going here, a rho dB going here, and a rho dB going here, right? And that would form a cone over A of D. But there's actually another cone we can find, also going from P into the arrow diagram of D. And this one is a little trickier to find, but if you think about it, we need to find a way to get these morphisms back, right? The commutativity properties of these morphisms back. We need a limit over D here. And a limit over D is a cone, so it has to commute with all of the morphisms in the diagram. So we need to somehow recover the information that we have in these morphisms here, since now we have only objects. Well, what if we took all the morphisms that we got from projecting into D and then following the morphisms in D, right? So say we start in P, we project through some row dA maybe into dA equals dC, so we're going from P into dA dC, and from there we just follow all the possible morphisms, right? So the first morphism we'd get would be d alpha 2 after row dA, and then the second morphism we'd get would be d alpha 1 after row dA, right? And similarly for every possible morphism in this diagram. Here we only have 2, but maybe we'd have more. Well, we'd end up with the collection d alpha after row I, and that would be for some alpha, or for every alpha, going from I into j, right? So we project into the domain, row dA, and then from there we take a morphism in D, the diagram. Well, then based on the way we constructed the arrow diagram, this collection is basically going to be the collection of legs in a cone, right? There's going to be one for each object in the arrow diagram. Why is that? Well, because we selected the number of copies based on the number of morphisms that entered that object, based on the number of morphisms that had that object as a codomain. So basically, each time you're going to pop in with your row I, and then say for dB here, well, the first one might be the identity. So I take row dB, and then I follow the identity back to dB, right? Well, maybe that's my first leg. Then the next leg, I go row dB, and then I follow d alpha 2 maybe this time, right? And maybe that's the second one. And then I follow row I into, or row dB into dB, and then I follow d alpha 1, right? And maybe that's my final leg. But so thanks to the way we counted the number of copies, we're going to have exactly one for each object in this diagram. And so we're going to get another cone over AD, which also has vertex P. So let's add this cone to our proof as well. So we can say that P, and then maybe call it tau Jn, is a cone over A of D, where tau Jn is equal to d alpha after row I for all of the alpha morphisms from I to j in J. So for any j, the n here is basically iterating over all of the morphisms alpha that have that j as a codomain, right? So basically you have the in degree of dj is the maximum n, and then you just iterate. For each j, you iterate over all of the n's, which is iterating over all of these morphisms which have codomain j. And this forms a cone because n is the in degree of dj for each dj, and we constructed the arrow diagram to have exactly n copies, right? The number of morphisms coming in, or the in degree of dj, is the number of copies of dj that we have in the diagram, the arrow diagram. So we have two cones which are both over the diagram of arrows of D, and since Q here, curly Q, is a product over that diagram, we need a mediating morphism for each one of these cones, right? That's what it means for it to be a product or a limit. So we need to have a unique mediating morphism, maybe call it S, going from the vertex of our cone to the vertex of the product over A of D. So that would mean to go from P to Q. And it needs to be such that the legs of the product commute with the legs of the cone. So we would need to have that rho Jn would need to be equal to pi Jn after S. And similarly, we'd need to have the mediating morphism for this cone, right? One for this, a unique one for this cone, and a unique one for this cone. So maybe that one's called T. Going, again, it's the same vertex and the same product, so it's also going from P to Q, such that, again, the legs commute. So that gives us that tau Jn is equal to pi Jn after T. And again, it's important to keep track of these indices here. This is over all j for every object j in our index category j here, and over all n, where n just counts up to the in degree of dj, right? Which implicitly means we're iterating over all of the morphisms in j which have codomain j. I've repeated that a couple times, but it's important to keep track of all that. So we'll add for all j and for all n here. So to add this to our diagram, we found two cones, both over AD coming from P. So one leg for each of these connections here. And so if that's the case, we must have two mediating morphisms. S and T, both going from the vertex of those cones to the vertex of the product, because that's what it means to be a product. Well, what does that mean? Maybe pause the video here and think about what the next step in our proof might be. What did we just find? We just found two parallel morphisms, right? S and T, and we said that our category C here has equalizers. So if we have two parallel morphisms, we have a candidate diagram for an equalizer. And since our category has equalizers, that means there needs to be some equalizer, maybe call it E here, for the diagram containing S and T, these two parallel morphisms. So let's add that to our proof as well. So E consisting of E and E, which goes from the object E into our cone P, or into the vertex of our cone P, is an equalizer for S and T, which means that S after E equals T after E. And for any other morphism in the category which right equalizes S and T like this, there needs to be a unique mediating morphism going from the domain of that morphism into E here, our equalizer object. Well then, E lands in P, so we can add E on the right-hand side on both sides of this equation. So we can say that rho Jn after E is equal to pi Jn after S after E. But if that's the case, this side is just equal to rho j after E, right? This is rho j by this equation. Rho j after E. And this side, because S after E is T after E, is just pi Jn after t after e. But then we can also do it with this equation here. So we have that tau jn after e equals pi jn after t after e. But if that's the case, well, tau jn is d alpha after rho I. So this is d alpha after rho I. And that's after e. And this side is pi jn after t after e. And this is, again, for all alpha from I to j in our category j, right? For any alpha, we're iterating over all the alphas in j, all the morphisms in j. And if that's the case, well, look, this is the same side on both equations. So we can say that these two sides are equal. So we get that rho j after e is equal to d alpha after rho I after e. But what is this equation saying? It's basically saying that the composition of the equalizer morphism E with the projections of P commutes with all of the morphisms in the diagram, right? Because this applies to any morphism in the diagram. So basically it's saying that you can use the composition of E and rho I or rho j, depending on which component you're looking at, to form the legs of a cone. And not only that, but there's obviously going to be exactly one for each dj, right? So what we've said is that actually E and then the composition of rho j after E for all objects j and j is a cone over D. So we've found a cone over D, so let's call it L, so that hopefully this will be our limit, right? We found a cone over D, so let's explore whether this cone is a limit or not. Because if we found a limit, then we're done, right? That's what we needed to prove. So we can add this cone to our diagram. So what we're saying is that E and then the composition of E with these projections here, the row projections, form a cone over the diagram D, right? Because these go into the same codomains. So it's like as if we had a cone over D. So what do we need to prove in order to finish the proof? We need to show that if there's some other cone, maybe call it X over D, so having one morphism going from our vertex X and with commutativity for all morphisms in the diagram. So maybe this is X dA and this is X dB. So if we have this cone X, XdA, XdB, where all of these triangles commute, then we must have a unique mediating morphism going from the vertex of our arbitrary cone to the vertex of our hopeful limit here, or of the cone that we originally found, which again consists of E, and then this is rho dA after E, and this is rho dB after E. So to continue with the proof, let L be the cone that we just found and that we proved was a cone, and let curly X be some other arbitrary cone over D. So that is a vertex X and the legs xj, each going from the vertex X into the dj in our diagram D. And our ultimate goal will be to show that there's a unique mediating morphism going from X, the vertex of this cone, into E, the vertex of our L here. So for reference, I've just written all of the equations that we've come across so far in the proof. And just a reminder that this is for all alpha going from I into J in our index category J, and where the n's iterate over those alphas for each j. Well, let's notice two things about x here. First, if it's a cone over d, then it has to also be a cone over what? N of d, right? Because d and n of d have the same number of nodes, and there's one going into each from x, and there's basically just less restrictions on this diagram, right? Because there's no commutativity requirements like there is in our original diagram, D. These legs need to commute with all these morphisms. But in this diagram, we don't have any morphisms. So it's basically easier to be a cone over this diagram. So x, curly x, must also be a cone over n of d. Like this. And second, if it's a cone over n of d, then we can apply the same trick we did to the product here to get a cone over a of d, right? Because we just repeat the same component anytime there's another copy in this diagram. So basically, there's a cone with vertex x over all of these diagrams, d, n of d, and a of d. So let's write that out a little more rigorously. First, we know that curly x is also a cone over the node diagram, or the diagram of nodes of d. And two, we can define x prime a cone over a of d, where we just do the same trick. We say that x prime is equal to x, and now it's x for every j and every n, where xjn is just xj for all j and for all n which are less than the n degree, the in degree of that dj. Same trick exactly that we did with p to get a cone over a of d, we apply it to x to get a cone over a of d. But if we have a cone over n of d and a cone over a of d, then we have a couple of unique mediating morphisms as well, right? Because we have a product over n of d and a product over a of d. So first, we need a unique mediating morphism going from x into p. Maybe call this one u. And then we also have a unique mediating morphism going from x into q. Maybe call that one v. So here we have our two unique mediating morphisms, u and v. U being the unique morphism that makes x of j equal to rho of j after u, and v being the one that makes xjn equal to pi jn after v. But actually, s after u and t after u both satisfy this equation as well. So let's see that. Pi jn after s after u is equal to rho jn after u, right? This pi jn after s is equal to rho jn according to this equation. And then we have rho jn is just always equal to rho j after u. So it's not rho j after u, but rho jn is always equal to rho j, and that's after u. And that is just what commutes with the legs of our cone x, right? So that's one of the xj's. So, and also the same for t after u. Since pi jn after t here is equal to tau jn, and tau jn is equal to d alpha after rho I. So this is d alpha after rho I, and then we have our u left over here. But again, this is what commutes with the legs of the cone x, so this is d alpha after xi. But if that's the case, remember that it has to commute with all of these d alphas, right? This cone, these legs have to commute with all of these d alphas. So effectively, if we have d alpha after xi, that has to give us the same thing as if we just go straight from xj, because alpha goes from I into j, in j. So s after u and t after u both satisfy this equation. They're both equal to xjn. But there's only one morphism that can satisfy that equation according to this. So we have that v has to be equal to s after u, which has to be equal to t after u. But then look, s after u is equal to t after u, and EE is an equalizer for S and T. So U right equalizes S and T, and that means we need to have a unique mediating morphism theta going from X into E, the object of our equalizer. So there's a unique mediating morphism theta going from X into E such that E after theta is equal to U. But then we can add rho j, any of the rho j's, to both sides to get rho j after E after theta is equal to rho j after U. But rho j after u, remember again, for the third time, is just what commutes with the legs of xj. So this is xj. And remember, these are the legs of our L here. And these are the legs of x. So basically what this is saying is that theta commutes with the legs of L and the legs of x for every j, which means that it's a cone morphism. Theta is a cone morphism going from X into L. So we do have a potential mediating morphism. We just have to show that it's unique, right? To be the unique mediating morphism. So suppose there was some other theta prime that also made these legs commute. So rho j after E after theta prime is equal to xj as well. Well, then notice that both of them satisfy this equation, right? E after theta can be substituted for u here, and E after theta prime can be substituted for u here. But once again, u is the unique morphism that satisfies this equation. So that means that we must have u equals E after theta equals E after theta prime. But remember, we had a video on equalizers where we showed that equalizers are always monic, which means they're left cancelable. So we can cancel these, and we can say that theta equals theta prime, and that means that this cone morphism, the candidate mediating morphism, is unique. And so we have found the required mediating morphism, theta, going from x into L, right? And so we can say that we do have a limit over D. The limit over D is L. And that gives us QED. So to state the theorem again, suppose C has equalizers and D is a diagram in C, then if both the product over the diagram of nodes of D and the product over the diagram of arrows of D exist, then the limit over D itself exists. This theorem allows us to conclude a couple of corollaries immediately, and in order to do that, we just need a couple quick definitions. So first, a complete category is one in which every small diagram has a limit. And what is a small diagram? It's one where the index category here, the set of objects in that index category, form a proper set. They're not a pure class. They form a set. And finitely complete category is one where every finite diagram has a limit. So the set of objects in the index category J is not only a set, but it's a finite set. And it turns out that these complete categories, ones where every small diagram has a limit, are actually more interesting than categories where every diagram has a limit, including ones where this forms a pure class, not a set. The first corollary says that C has equalizers and small products if and only if C is complete. And it's sort of a generalized version of this argument, right? Because it says if we have equalizers and all small products exist, so that means that N of D and A of D both exist for a small diagram in the category, then that diagram will have a limit, right? By this argument. And the other direction is really easy, right? Because if every small diagram has a limit, then we have equalizers and small products, because those are both different types of limits. And finally, in a previous video, we had already proved that C has equalizers and finite products if and only if C has pullbacks and terminal objects. And remember, it was finite products in this case because pullbacks is for two colliding morphisms, not an arbitrary number of colliding morphisms. And so this theorem here allows us to add sort of a third equivalent condition to these two, which says that C is finitely complete, right? And that's just because this top part here, C is finitely complete if and only if C has equalizers and finite products, is just the finite version of this argument, right? So it allows us to give quite a nice, general, and sophisticated theorem.